analysis of transient heat transfer in a composite wall with two different layered materials. The wall is made of concrete on the left side and a copper alloy on the right, and the left side is exposed to hot ambient air. Concrete is a weak thermal conductor, while copper is a highly conductive metal. The material properties are described on the slide. The assumption is that convection on the left boundary and conduction within the wall are the only modes of heat transfer in the system because the right boundary of the wall has negligible convection since the ambient air is only exposed to the left boundary of the wall. Next, this problem uses one-dimensional heat transfer in the x direction, since the height of the wall is much larger than the wall's thickness or width. Another assumption is that no internal heat is generated, later reducing a term in our energy balance, and lastly, energy is conserved. The convection term is based on Newton's law of cooling, and this equation corresponds to the heat entering the system by convection. The conduction term is based on Fourier's law, and it is important to note this negative sign since the heat flows down the temperature gradient. The heat conduction equation can be derived using an energy balance and Fourier's law. The energy generated is Q times delta X, delta Y, delta Z, and the energy stored is rho Cp delta X, delta Y, delta Z times the partial change in temperature with respect to time. The heat flow rate was previously defined by Fourier's law, and plugging all of these values into the top energy balance equation and simplifying results in the general heat conduction equation, which is the density of the material multiplied by specific heat capacity and partial derivative of temperature with respect to time, equal to K times the gradient squared temperature plus the volumetric heat generation. The convection boundary equation is based on a heat balance. For the wall, the rate of energy stored is equal to the rate of heat in minus the rate of heat out. To find this, I define a small slice of wall thickness, delta X, and area A. And I started with the thermal energy equation, where thermal energy equals mass times specific heat times temperature. I substituted mass with density times area times thickness, and took the derivative of that to obtain the rate of energy storage, right here. Next, I combined all convection and conduction terms into a total energy balance. These derived equations cannot be solved directly, so I have switched them to finite difference form, which transforms the calculus into simple algebra that a computer can solve in a loop. I started by dividing the wall into nodes spaced by delta x and time into time steps of delta t, so that capital T subscript I superscript n represents the temperature at location I and time n. For the conduction equation, I used central difference for the spatial derivative and forward difference for the time derivative to rearrange the equation below, which I then rearranged again to solve for the temperature in the next second, shown here. In the convection equation, I used forward difference to simplify both derivative terms and yielded a function where the temperature change is a direct function of the Biot and Fourier numbers. I used forward difference for the convection spatial derivative because at the surface, there is no left wall neighbor, so the code must be forced to look forward into the wall at node 1 to see how the temperature changes, despite the central difference being a more accurate method. Steps 1 and 2 of my code, I defined my chosen parameters and prepared the wall for numerical manipulation by dividing it into small slices, setting them all equal to the initial temperature of 30 degrees Celsius, and adding a stability guardrail to prevent the math from breaking. 3 is the solver, which is a for loop that marches the solution in small increments of time. At each iteration, the code calculates the new temperature for every point in the wall based on the convection and conduction equations derived earlier. I used the forward difference method to update the surface node according to the air temperature, while the central difference is applied to the interior nodes. At 15 millimeters, the code matches the heat leaving the concrete with the heat entering the alloy to keep the flow consistent. At 40 millimeters, it stops all heat flow to simulate an insulated end, allowing us to visualize the time delay as heat travels through the wall. The script that I used to plot. For the first graph, the left surface temperature spikes immediately because it is the only part of the wall exposed to the hot ambient air, while the right surface does not increase in temperature until later when the heat has traveled through the entire thickness of the concrete and the alloy. The middle graph displays the center temperature versus time, which is not an exact average of the two surface temperatures since heat moves much faster in the alloy than it does in the concrete. The graph on the right shows the spatial temperature of the block at different times. As shown, temperature decreases with position as heat always flows from hot to cold. Temperature also increases with time since the hot heat source, aka the ambient air, remains. The energy of the wall rises with time. Also, notice the slope is steeper in the concrete and flatter in the alloy. This is because concrete is a poor conductor and needs a larger temperature difference to move heat, whereas the copper alloy is conductive and needs much less of a temperature difference to move the same amount of energy. The next part of this project is to run a simulation until the earliest of these three conditions occur. 1. The center of the wall reaches a target temperature of 60 degrees Celsius, which is a typical and realistic midpoint for heat penetration, and a common activation temperature for chemical processes. The second stopping criteria would be if either surface exceeds a maximum temperature of 105 degrees Celsius, which protects the concrete from thermal spalling before the heat reaches the core. Lastly, the third condition is if the time exceeds 2 hours, which is a standard production window to ensure process efficiency. The first part of my code defines geometry and properties of the wall and environment, as well as the stopping conditions. I created a digital grid and an X array like before to divide the wall into slices and create a coordinate system. I also defined thermal diffusivity, which calculates how fast heat diffuses through the the solver, which runs on a while loop, which first ensures the current time is less than the maximum time, otherwise the loop would stop. And in the loop, the same heat equations from part 1 are solved, stored, and for each forward step, the conditions are checked with an if statement below. The last part of the code assimilates this information onto a graph. Condition 1 was met first as the center of the wall reached the target temperature of 60 degrees. This happened first since once the heat fought to get through the first 15 millimeters of concrete, it hit the highly conductive copper alloy, which spread the heat to the center almost immediately. Additionally, since the ambient air temperature is 110 degrees Celsius and the safety limit at the surfaces is only 105 degrees, the push toward the safety limit is weak as the surface gets hotter. In a different simulation that I ran, the surface temperature maximum was hit when there was A, a thicker concrete layer, B, a hotter furnace, or C, a high convection constant. In this simulation, however, the conditions of the wall allow for the center to reach the desired heat without the left surface becoming dangerously hot, which is a safe heating process. The last thing to do is compare our results to a lumped capacitance model. This type of model assumes a uniform temperature throughout the wall at any point in time, defined by an energy balance, which simplifies to the equation here, where tau equals 1 over A multiplied by the total thermal capacity of the wall. To decide if this model is valid, you must calculate the Biot number, which represents the ratio of convection or surface resistance to conduction or internal resistance. If the Biot number is greater than 0.1, then a significant temperature gradient exists and the lumped capacitance model should be rejected. This is because the error in the lumped capacitance approximation is roughly proportional to the Biot number, and 0.1 is a realistic error boundary given by the constraints of this problem. Lastly, since the wall is composite, I calculated the total thermal capacity, which is the density times volume times specific heat of the concrete plus that of the alloy. This model calculates the total thermal capacity of the wall and the equivalent thermal conductivity of two different materials, treating the alloy and concrete like resistors in series to find a single Biot number for the entire wall. The solver relies on the first-order differential equation derived from the energy balance earlier, as the rate of heat entering via convection must equal the rate of energy storage in the wall. Lines 105 to 106 represent the integration of this energy balance. The code solves for the invent time by treating the wall as an exponential system rather than a linear one, since thermal driving force decreases as the wall heats up. Finally, the code performs a sensitivity analysis by comparing the idealized time against the actual time recorded by the finite difference simulation. The results showed a Biot number of 0.231, which is higher than the limit of 0.1, rejecting the lumped capacitance model. The lumped prediction time was 10 minutes faster than that of the distributed model due to the thermal lag from the concrete's low conductivity. The percent error between the two models is 17%, which is a significant amount in industry. Ultimately, the lumped capacitance model underpredicted the time it would take for heat to travel through the wall. My sources, thank you for watching.